of random matrices. And of course, to be able to study the spectral properties of random matrices, you have to have some model of what the randomness in the matrix looks like. And the classical kind of models that are considered in random matrix theory are, tend to be very simple models that have very complicated and beautiful asymptotic behaviors. Okay, so exact asymptotics. So what's a typical model of random matrix theory? You take a D by D matrix, you fill it with IID entries. Now, if I do this in every dimension, I just take the same distribution of the entries and I just increase the dimension. I get naturally a sequence of random matrices of larger and larger dimension. And now we can study the asymptotics of the spectrum of the eigenvalues of those random matrices, and we can try to compute all sorts of things about them. And, such models have been studied, for I guess almost a century now, and the sheer level of detail in which these are understood is absolutely breathtaking. I mean, they have beautiful structures in them. So just as an example that we will often think of as a guiding example, right? If I take a D by D matrix X, self-adjoint matrix X, right, whose entries have mean 0 and variance 1 over D, okay, up to symmetry, right? So Xij is equal to Ji, but otherwise are IID, right? So I fix the distribution and I let the dimension go to infinity, and then you can ask, what does the spectrum do? And the most classical results in this area is that if I draw a histogram of the eigenvalues, you start seeing this beautiful semicircle distribution. So the histogram of the eigenvalues behaves deterministically as the dimension goes to infinity. You see this wonderful semicircle distribution. And the largest eigenvalue converges to 2, and the smallest eigenvalue converges to -2. And okay, and we go from there. But for these kind of models, we understand in much greater detail how they behave. You can zoom in on the eigenvalues at the level of the spacing. You can compute all of the exact limiting distributions, et cetera, et cetera. Okay, so this is a very classical model. Now, as opposed to classical random matrix theory, what is non-asymptotic random matrix theory that is in my title? Well, actually, it can mean many things, and different people have used this term in different ways. So one way in which you can view this question of non-asymptotic random matrix theory is to make the asymptotic theory quantitative in a certain sense. And so you can ask, for example, in this setting, let's say I have IID entries, but they're, let's say, sub-Gaussian, or I have some specific bounds in their moments. And can we now understand for a fixed D by D matrix how close we are to this limiting situation, and what can we say about those kind of things? Which, of course, it does not sound super exciting, but in fact, one can say very deep things this way. And in particular, these kind of questions are very useful, because if you are not studying random matrix theory for its own sake, but you're using this as input to something else, for example, you're studying the behavior of some numerical linear algebra algorithm or something like that, then you really need to have some explicit control about a finite matrix in order to be able to use that as input for the remainder of the analysis, right? So one would like to have some kind of quantitative, explicit, effective bounds that explain in terms of what is known about the distributions of the entries, what we can say about the eigenvalues. So this is one kind of direction in non-asymptotic random matrix theory. But there is another one which, for me personally, which I have been interested in for many years, which is that if you view the questions that we're asking non-asymptotically, you can study models that are much more general, that are outside the reach of classical random matrix theory. And you can consider much more general classes of models. So let me give the kind of guiding example that I have in mind for that. Suppose I give you a D by D self-adjoint random matrix. I make these matrices self-adjoint just so they'll have real eigenvalues. It makes it easier to talk about them. But if you want to talk about the singular values of non-self-adjoint matrices, it's just as easily done. And what am I now going to assume? I'm going to assume that the entries are jointly Gaussian. And that's it. So I'm assuming the entries are jointly Gaussian, so I have a Gaussian random matrix. But otherwise, the entries can have any mean, and each entry can have its own mean. They can have any variances that you want. They can have any covariance that you want, right? So this is an extremely general class of random matrices. It's very far from the kind of random matrices you see in classical random matrix theory. It can be anyway, right? Because you can have basically arbitrary kinds of dependencies between the entries. You can have arbitrary kind of patterns of variances as you go across the matrix, etc., right? So these kind of situations are much more general than if you're looking at one specific model and you're trying to study its asymptotics. And in particular, if you look at these kind of models, you have to do non-asymptotic random matrix theory because asymptotic random matrix theory doesn't even make any sense, right? I fixed some D by D matrix. I've given you some fixed pattern of the entries. There is no natural sequence of matrices of increasing dimension here that we can argue behave the same way, right? If I've given you one particular set of variances and means of the entries, it is what it is, right? So such matrices can only be studied in a meaningful way in a non-asymptotic sense, right? And that means that rather than looking for asymptotic results, we have to have quantitative inequalities that tell us something about the behavior of the eigenvalues of such matrices. So at this level of generality that I've written here, there is a classical result that you might want to keep in mind. So suppose in addition, so in this example, what happened to my pen? I turn to eraser. In this result, so I'm taking the Gaussian random matrix with mean 0, just for simplicity. Okay, so it's this example I wrote up here, but with mean 0. There's a classical result which is called the non-commutative Kinshasa inequality, though it wasn't phrased this way originally. I think it was realized in the paper of Mark Rudelson that one can extract this kind of information from it, and it's been developed a lot since. So let's say we want to understand the edges of the spectrum. So when I write a norm of a matrix, I always mean its largest singular value, or the largest absolute value of the eigenvalues. So I'm just trying to understand roughly the range of the spectrum, right? How spread out are the eigenvalues? So it's not hard to see, this is basically Jensen's inequalities, that I can lower bound this by the norm of the expectation of the matrix squared. And the beauty of this quantity is that this just depends on the covariance matrix of the entries, right? Because I've taken the expectation of the square of the matrix first. So the quantity here on the left-hand side is something that's explicitly computable on the basis of the data that defines the matrix. Whereas the quantity over here, this is a highly nonlinear function. This says something about the eigenvalues of the matrix. So this is a highly nonlinear function of the matrix. So that's something that's hard to compute. But the beauty of these inequalities is that they say that this simple lower bound can be reversed up to only square root log d. Right? So if I'm willing to pay a factor square root log d, then I can reverse this bound and I can compute up to a factor square root log d the range of the spectrum of such a matrix. And the beauty of such a result is that, I mean, the assumptions are I said mean 0, but even I can make this for non-mean 0. It's trivial to extend this to non-mean 0 situation. So other than that, I've taken a completely arbitrary Gaussian random matrix. I've made no assumption about the independence of the entries. I've made no assumption about the pattern of the variances, about the pattern of anything, right? And yet I'm able to say something very meaningful about the spread of the spectrum in such an extremely general situation. So one can imagine such an inequality is a very powerful tool to be used in other problems. Right? On the other hand, if you look at the left and the right-hand side, even though there's only a logarithmic factor in the dimension, right? So for example, if you talk to a computer scientist, they would say that's basically O of 1, right? But at the same time, you know, log d goes to infinity, right? So as the dimension goes to infinity, the left and the right-hand side of this inequality diverge. Whereas in classical random matrix theory, typically as the dimension goes to infinity, we understand the matrix better and better and better, not worse and worse and worse, right? So these inequalities give you very, very weak information compared to the kind of beautiful theory you get in classical random matrix theory. But nonetheless, these inequalities are very powerful and they're very useful in application. Now, I want to make a slight detour here and say that very recently in work with, let me go to the next page. Very recently, in work with Afonso Bandeira and March Budiarjo, we made a huge amount of progress in understanding Gaussian random matrices. And we managed to get inequalities, managed to get sharp inequalities for Gaussian random matrices. Sharp in many cases, in many cases that are of practical interest. And what I mean by sharp is, you see here in this bound, for example, you have the expected norm of x is upper and lower bounded by some factor times something computable, but the factor is diverging in the dimension. But in these sharp inequalities, we can actually, for many random matrices, prove bounds that look like this, minus something which I don't want to define in this talk, but which is explicitly computable based on the mean and the covariance of the entries, by something small. And by small, I mean something that in many cases is much smaller than this over here. And this is also a nonasymptotic inequality. And the reason I'm saying it so vaguely is because I don't want to actually talk about this topic in this talk. But I just want to indicate that we have now, as a consequence of these kind of results, a very general theory that explains nonasymptotically how many Gaussian random matrices behave. And this theory allows us, as a kind of black box, to study lots of random matrices that are outside of the scope of kind of classical random matrix models. But all of these random matrices are Gaussian. And in the proofs of these results, we use heavily the Gaussian structure of these matrices, and we use heavily the tools, the Gaussian tools that we have at our disposal when you're dealing with Gaussian random variables. And similarly with more classical results on nonasymptotic random matrix theory, right? Not just the non-commutative Kinshasa inequality that's written over here on this slide, but also on in results about the largest, the smallest singular value, and all sorts of wonderful results that appear in the theory of nonasymptotic random matrix theory. Often one starts off by proving results either for Gaussian random variables or for sub-Gaussian random variables, where you have very nice controls of the tails of the distribution. And then after that, if you want to prove something in more general situations, you might have to work quite hard in order to get in order to get results that apply in situations that are very far away from this Gaussian situation. And in fact, a lot of work in nonasymptotic random matrix theory goes into trying to adapt the proofs of the results that one proves to new situations where you have much weaker distributional assumptions. And this can be a lot of work, and there can be new phenomena that appear when you do this, right? And typically it can become very technical to do so. Okay, but in this theory that I'm describing very badly over here, we in fact don't even know how to prove such theorems directly for non-Gaussian distributions. It doesn't seem the proofs seem to make heavy use of the Gaussian assumption. So what I want to discuss in this talk is a different viewpoint on this problem. And the viewpoint was directly motivated by trying to extend the theory that I'm describing on this slide to non-Gaussian situations. And the basic point of view I want to explain is one that is actually very well known in classical random matrix theory, which is the notion of universality. So the universality principle says that many non-Gaussian random matrices behave just like Gaussian random matrices. Now, of course, what does it mean? I mean, you could say that actually any non-Gaussian result, or most non-Gaussian results in random matrix theory, implement this one way or another, right? Because say I've proved something for Gaussian random matrices. Well, now I can work very hard to adapt the proof to non-Gaussian situations. And if I get a similar outcome, then I've proved that the same phenomenon holds for non-Gaussian random matrices. But what the viewpoint I'm promoting here is to not try to do it this way. Don't try to reprove the things that you prove for Gaussian random matrices for non-Gaussian random matrices. Rather, let's just try to show that the behavior of a non-Gaussian random matrix is like a Gaussian random matrix without trying to understand how the Gaussian random matrix behaves. In principle, those are two separate phenomena, right? A non-Gaussian behavior random matrix could behave like a Gaussian random matrix. And then you could try to understand how the Gaussian random matrix behaves as a separate step that's independent of trying to show that the non-Gaussian, the Gaussian random matrices behave alike. And this point of view is very, it's very natural in classical random matrix theory, and there's a huge number of breakthroughs that have been made there in understanding universality. But somehow in non-asymptotic random matrix theory, this viewpoint doesn't really seem to have been explored, at least to my knowledge, to any great extent. Typically, non-Gaussian results are obtained by starting with results that hold in sort of in nicer situations and trying to adapt the proof so you get better and better, so you can assume weaker and weaker things. So what I'm going to try to explain to you is that, in fact, we can do in this kind of very general situation that I described before, in the case of non-commutative kinship inequality, and in the case of these non-commutative inequalities that we now have, that we can actually implement this universality principle in a non-asymptotic way. And this non-asymptotic implementation of the universality principle, the nice thing about it is that once you have it, it's a black box. And it turns out that many problems that are otherwise might be very difficult, you just kind of like hit it with this hammer, and you will get answers very easily from them. Okay, so now, of course, you cannot do magic. You cannot get extremely deep things from a general principle. But there are many things that are very easy to get from such a principle that otherwise, if you were trying to just adapt the proofs of those kind of results, you would have to work much harder and they would be much more painful. Okay, so I hope that I'll give some examples that will make this clear. So let me try to make progress towards describing what such results look like. So the first question that you should ask, of course, is I'm talking about Gaussian random matrices and non-Gaussian random matrices. But it's like there's a famous quote which is heavily abused, of course, by Tolstoy, that all happy families are alike, and all unhappy families are unhappy in their own special way. And you could say it's the same thing in this situation, right? I mean, Gaussian random matrices form a very nice, very clean class of matrices that allow you to have dependence between the entries and allow you to have non-homogeneity. But if I now say, okay, let's take non-Gaussian random matrices, I mean, that's basically any matrix is a non-Gaussian random matrix, right? I mean, it seems too general to work with, right? You need to have some kind of distributional assumptions on the matrix in order to be able to say anything meaningful at all, right? So I need to introduce a kind of non-Gaussian model that, on the one hand, is concrete enough that we can make progress, and on the other hand, is general enough that it captures many interesting applications at the same time. And the natural model that we will work with is one that we most certainly did not invent. We will simply go back to this classical non-commutative kinship inequality at the bottom of this slide. This Gaussian result, which dates back in some form or other to the 1980s, it holds for Gaussian or for random matrices close to Gaussian in a certain sense. But in recent years, this result has been generalized to a very large class of non-Gaussian matrices. And these generalizations, they go under the name of matrix concentration inequalities. And they were heavily popularized by Joel Trupp, who developed many results in this direction. Early results on this were also by Oliveira. And many people have worked on these kind of results. And the idea behind these results is that the same phenomenon that goes into these, into the non-commutative kinship inequality, right? So generalize the inequality that the expected norm of X for a Gaussian random matrix is bounded by square root log D times this very natural quantity to a large class of non-Gaussian matrices. And of course, the way they do it is like I explained before, they adapt the proofs of these kind of inequalities to the non-Gaussian setting. But the nice thing about them is that they have identified a class of non-Gaussian random matrices that seems to show up over and over again in applications and that models many different interesting phenomena. So we're going to adapt, we're going to work with the model that is used in these kinds of inequalities. And what is that model? So what they do is they take random matrices that look like this. I'm immediately going to depart from what they do in allowing myself to have a mean. So this is non-random. right? So A is just the mean, the expectation of the random matrix. This is non-random. And then I'm going to take the mean zero part. This is just the sum of some finite number of mean zero random matrices. Of course, I mean, if I take big N equals to 1, I've just described every random matrix, right? So you should be a little bit suspicious when you see a model like this. I'm not assuming anything about the ZIs except that they're just independent random matrices, mean zero independent. They don't have to be IID. They don't have to be, they don't have to have the internal structure. They just mean zero independent random matrices. So if I take big N equals 1, I've described every random matrix. But of course, if I take big N equals 1, then the inequalities are not going to say anything. They're going to become trivial. So what kind of inequalities do they prove? So let me show you a very powerful inequality that you get for this class of random matrices. Well, before I do that, let me just emphasize that, so these random matrices are non-Gaussian because the ZIs can have basically any distribution, right? But they capture many random matrices as special cases. So for example, just to give you two examples, any Gaussian random matrix is a special case, right? Because any jointly Gaussian variables can be written as linear combinations of independent Gaussian variables, right? So if I have any Gaussian random matrix, I can write it like this, I is 1 to n, with some deterministic matrices AI and GI are just IID standard Gaussian variables, right? So in fact, the jointly Gaussian matrices are just a special case of these kinds of random matrices where the ZIs are just the deterministic matrix times a scalar Gaussian variable. On the other hand, any random matrix with independent entries is also of this form, right? Because I can write X being the mean plus sum over I and J of the entry, the IJ entry of the matrix times the matrix which has a 1 in the IJ coordinate and 0 everywhere else, right? And these are independent because I assume the entries are independent. And now they can have arbitrary distributions, right? So these are kind of two extreme cases, right? Any Gaussian random matrix, they can be heavily dependent, but they're Gaussian, or any matrix with independent entries, but with arbitrary distribution. These are two kinds of cases that would naturally arise in such situations. And they're both very simple special cases of this general structure. But again, there are many kind of dependent situations that are captured by this, like sample covariance matrices are, for example, a very natural class of matrices of this form. And we will see some other examples later on. Hopefully, I will have time. So it turns out that this kind of model, that there are many random matrices that show up in applications that are fall into this general structure. So what can you show about such random matrices? Well, so I'm going to write down the kind of simplest extension of this inequality to this larger class of random matrices. So this is called the matrix, or it's a form of at least the matrix Bernstein inequality. In this form due to Oliveira and Trop. So remember, for the Gaussian case, we have this inequality, and let's say mean 0 for simplicity. So for the Gaussian case, we have that the expected norm of x is bounded by square root log d times the expectation of x squared with the square root. So for the non-Gaussian case, right? So the non-Gaussian model here again is x minus the expectation of x. Expectation of x is here 0. Is sum I is 1 to n of zi, where zi are independent random matrices. Well, what you get is you have exactly the same inequality, but you get an extra term, and the extra term captures the non-Gaussianity. So here you have a log d times some parameter called r. And what is the parameter called r? R is just the maximum size of these summons. Maybe I'll take the uninfinity norm. Let's say I assume they're all bounded, right? And I just take the maximum norms of the summons. So you see, if big N equals 1, if I take just one summand, I've described every random matrix. but then R would just be equal to the norm of X, and there would be nothing, or the L infinity norm of the norm of X, and it would the inequality would be useless. Right? But in general, this inequality is interesting in situations, roughly speaking, where the n, the number of summons, is rather large, right? So this quantity over here, this is the expectation of the square of the matrix. The size of this will be something like the sum of the squares of the zi's, right? So it's a sum of n terms. But this guy will just be the maximum size of the zi's, right? So as soon as each zi is of smaller order than the sum of this, or each zi squared is of smaller order than the sum of the squares, we expect this R parameter to be much, much smaller than this parameter over here, right? And in that situation, basically, this bound behaves exactly like in the Gaussian case, right? So the way you should read this inequality, the inequality is proved by adapting the proof of the Gaussian case to this model. But the way you should read this inequality is that this inequality just says that the behavior is like the Gaussian case, plus an extra term, which captures the deviation from being Gaussian. And the parameter that measures the deviation from being Gaussian is just the maximum size of the summons in this model over here. The maximum.
Just a quick question. Why this extra term disappears in Gaussian case? L infinity is kind of infinity in Gaussian case, right?
Well, I've written here an L infinity version. There are versions of this which work in LP. Okay, so first of all, this L infinity, you can replace it by log D if you wanted. That wouldn't make much difference. And then it's called matrix Rosenthal inequality. Really, I mean, if you type matrix concentration inequalities in Google, then you will find 1,000,001 variants of these inequalities under different distributional assumptions. They all have the same kind of conceptual structure, but you know, some of them are better in some situations than others. But the reason that there is no second order term at all in the Gaussian case, I mean, maybe is better explained by what I'm going to say next. Okay, but the first order term here is the Gaussian behavior. So whatever is the second term is somehow captured, you know, capturing the fact that we are no longer Gaussian, right? So there has to be some error. But in many situations, this error is very small. Of course, you know, the way you should think about this looks very much like the central limit theorem, right? If these were scalar random variables, then I take a sum of n independent scalar random variables. It's very well known from the Lindeberg central limit theorem that if I take a sum of independent random variables and each one of them is of smaller order than their sum, or the sum of the squares, then the random variable behaves roughly Gaussian, right? So you can view this intuition as a kind of central limit theorem intuition. But the remarkable thing about random matrices is that when I take this in higher and higher dimension, in the central limit theorem, typically the error has to depend polynomially on the dimension. So if you apply the central limit theorem to high dimensional vectors, you're typically going to get very, very bad results in high dimension. But for random matrices, it turns out that the error in this kind of central limit theorem only behaves logarithmically in the dimension. And that's kind of the magic of these type of results, is that the dimensional dependence is very, very mild. But even if you're in a situation when the second term is negligible, you still have all of the drawbacks of the Gaussian bound, right? Because you still have this square root log D here, and in most situations, that's square root log D. In most examples, that square root log D shouldn't be there. So, you know, in most examples, this Gaussian bound is inefficient, and therefore the non-Gaussian bound is also inefficient. Okay. So, good. So, these things are known, but they're restricted in some sense to generalizing this inequality that we started with. What I'm trying to claim here is that, in fact, this fact that this works is just a manifestation of a very general phenomenon. I claim that when this parameter R over here is small, that simply implies that this non-Gaussian random matrix X behaves like a Gaussian random matrix X. And when you know that, you can apply whatever bound you like to the Gaussian random matrix. Right? So if you knew, for example, that when this parameter R is small, random matrix X behaves like a Gaussian one, then if you apply this result to a Gaussian one, you will recover that. But if you apply a better result to the Gaussian random matrix, you will recover a better result than the non-commutative, than the matrix Bernstein inequality. Right? So this is the change of viewpoint, right? The viewpoint of universality is, let's not try to explain how the Gaussian random matrix behaves. Let's simply show that the non-Gaussian matrix behaves like the Gaussian matrix. And then we can apply our favorite result to the Gaussian matrix to understand how it works. So let's write down some kind of theorem. Okay. So I'm working now again in this general model. So A is deterministic, and I take plus a sum. That's an n. All right, good enough. A sum of independent mean zero random matrices. These random matrices Zi are otherwise general. And let me make a definition. The Gaussian model of X is the random matrix G whose entries have the same mean and covariance as the entries of X. So I'm going to just, rather than trying to understand how X itself behaves, I'm just going to make a new random matrix G. And I think of G as a kind of model of how the random matrix X is behaving. G is a Gaussian random matrix, so its entries are jointly Gaussian. And I simply pick the means and the covariances of the entries of G to be the same as the means and the covariances of the entries of X. Okay, but G is Gaussian and X is not Gaussian. So we think of G as a kind of model for how X is behaving. Okay. And here is one very simplified form of a general theorem. So this is with my PhD student, Tatiana Bailovskaya.
Ramon, are the entries independent or dependent? Do we assume anything? Entries of the Gaussian, are they independent from each other?
No.
Okay.
They have the same covariance as the entries of X. So if the entries of X have covariance 0, all of them, then the entries of G will be independent. But if the entries of X do not have covariance 0, then the entries of G will not be independent. Okay. So this is an extremely general model. It captures many dependent situations. And this is a kind of simplified form of one of our results. But let me just for simplicity, let me cheat a little bit. Basically, what we're saying is we are not going to say anything about the norm of X. We're simply going to say that the norm of X minus the norm of its Gaussian model is bounded by some power of log. So in this simplified form, let me write log squared, then it's basically correct, times this parameter R that we had on the previous slide. R is just the maximal size of the Zi's. So you see, this theorem over here is saying nothing about how X behaves. It's only saying that X behaves the same way as this Gaussian random matrix, as long as R is small. But as soon as that happens, you can apply whatever bound you want to this Gaussian random matrix to understand the behavior of X, right? So the universality principle reduces the study of the non-Gaussian matrix to understanding a Gaussian matrix without, needing to know how the Gaussian random matrix behaves. You can use whatever tools you have at your disposal to understand the Gaussian random matrix. So you see, if you apply this theorem and then apply the non-commutative Khinchin inequality to the Gaussian random matrix, you will basically recover the matrix Bernstein inequality. If you actually use the result that I wrote here, you'd recover a slightly worse power on the log. But we have a version of this inequality that's more precise, where you recover even exactly the same powers on the log. So this extension that you see over here, which was originally proved by extending the proofs of the Gaussian result, you can just view this as a combination of the Gaussian result with the universality principle. But here in this inequality, the Gaussian result is often suboptimal. But in this result, if you have a good understanding of the Gaussian model, for example, even you understand its exact asymptotics, or you understand or you have the theory that we have, for example, with Bandera and Budiharjo, which gives you sharp inequalities, then you can apply those sharp inequalities to the Gaussian random matrix, and you will get much, much better results than what you can get from the matrix Bernstein inequality, right? And then basically what the universality principle is telling you is that once you understand how the Gaussian random matrices behave, you can just upgrade for free your understanding of non-Gaussian matrices, by applying the universality principle. So this is a slightly simplified form of a result. We have more precise results. Also, here I just wrote it just by analogy with the matrix concentration inequalities. I wrote it for the norm of the matrix. But we have similar results for all of the moments, for the resolvents. We have similar results for the smallest singular value, for the entire spectrum. So, really, one can apply these type of results. This is not restricted to studying the norms. Unlike matrix concentration inequalities, these kind of results are not restricted to studying the norms. You can use them to study most interesting aspects of the spectrum, at least at the mesoscopic scale. So the smallest singular value, the largest singular value, the spectral distribution, all of these things follow from variants of the same theorem. And all of them are non-asymptotic and all of them are quantitative. And what these results have in common is that this parameter R that showed up naturally in matrix concentration inequalities plays the role of the measure of Gaussianity. As soon as R is small, the random matrix X behaves like the random matrix G. Okay? And that's basically the message of these kind of theorems. So I don't want to give you now a laundry list of results. I'm just writing down one representative result to show you how these inequalities work and how they differ from the kind of classical theorems that we usually see in non-asymptotic random matrix.
Ramon, I'm sorry for interrupting.
Yes.
I think going back to my question, I still didn't understand it. It's right in definition. You say that G whose entries have the same mean and covariance as those. So it's just entries of Gij. Mean and covariance of these entries is the same as Xij. But what about between entries? There is some dependence.
That's why I wrote covariance, right? So what I mean here is that expectation of Xij equals the expectation of Gij, and the covariance of Xij, Xkl equals covariance of Gij, Gkl.
Yeah. Okay, I see.
And once I fix these two conditions have fixed the means and the covariances of the entries of the Gaussian matrix, then I've completely specified the Gaussian matrix, because a Gaussian random vector is completely specified by giving its mean and covariance. Right? So this definition defines the distribution of G. Does that make sense? Right. So if it were to be the case, as will be in my examples in a moment, but I'm just in my examples in a moment, this will happen to be the case, but it doesn't have to be the case. And I've only taken examples like this, so I wouldn't have to explain to you the Gaussian theory. But in the examples I'll have in a moment, the covariance between different entries of the matrix will happen to be 0 of X. The entries of X will not be independent, but it so will happen in those examples that their covariance will be 0. And then the Gaussian matrix will turn out to have independent entries. Right? But in general, it doesn't have to be the case. And, using new theory of these Gaussian random matrices, or even using non-commutative Khinchin inequality itself, right? We are able to also control many random matrices with dependent entries, right? So the theory is not restricted, has nothing to do with independence of the entries. Does it make sense? Okay.
Yes.
So in the rest of the talk, I simply wanted to just randomly pick some easy examples to show you how these theorems, what kind of things they say and how they work. Okay. And we actually wrote this paper some time ago, and we included one example in the paper to free probability, so to some results in free probability, so maybe a little bit esoteric, okay? But the paper was kind of long and we were happy with it. But it seems that it hasn't really been clear to people I've spoken to how to apply these results. So since then, I've collected a huge laundry list of applications because, the results are very easy to use. So I have this huge laundry list of applications. I've been meaning to update the paper, but, one has to teach and you lose track of time. So hopefully there'll be some updated version at some point with a whole bunch of applications. But let me just, discuss some particularly easy ones just for sake of example. So here's some random example that I like, even though it's not all that deep. Let me remind you of a kind of classical thing in classical random matrix theory. So let's consider the following Gaussian random matrix. So this is a Gaussian model. It's a very classical one studied, the asymptotics of which are studied in classical random matrix theory. Suppose I take a D by D matrix that looks as follows. I have a deterministic rank 1 component. So V is some vector in the unit sphere. Theta is just a number. It will become clear in a moment what it is. It's like the signal strength. Okay. And to this deterministic rank 1 matrix, I add just a standard Wigner matrix, 1 over square root D, right? And then I take here, I make it self-adjoint, but otherwise I take this to be IID standard Gaussian variables up to symmetry, right? So I make it self-adjoint, but otherwise up to symmetry. So this over here, the second part is just a standard random matrix that we saw on slide number 1, the classical model of random matrix theory that goes to the semicircle distribution, but they added to it a deterministic rank 1 perturbation. So this is a very famous model. It was studied by Baik, Ben-Arous, and Péchet. What happens in this model is called also a spiked Wigner model. What happens in this model? Well, if theta was 0, if this was just a standard model, then this distribution of the eigenvalues would be just a semicircle distribution, right? So it goes between -2 and 2. That's the classical behavior of the distribution. But now we added a rank 1 perturbation, right? So we added one extra eigenvalue somewhere, right? So the question is, where does that eigenvalue go? Well, if that new eigenvalue, right, if theta is very small, then probably that rank 1 perturbation will cause a new eigenvalue to appear somewhere here between -2 and 2, and you will not see it. You will not be able to distinguish it from the other eigenvalues of the random matrix, right? But if theta is very large, then you add a very large 1 rank perturbation, you would think that there would be a huge outlier eigenvalue that pops out of the bulk of the spectrum, right? You'd think that you would get a large outlier eigenvalue that sits over here. Right? And the question is, when does that transition happen? And it turns out that transition happens exactly when theta is greater than 1. So as soon as the strength of this rank 1 part is greater than 1, then an eigenvalue pops out of the bulk of the spectrum. But this eigenvalue doesn't sit at location theta. It turns out to sit at location theta plus 1 over theta. So for some reason, the addition of this random matrix deforms the location of this rank 1 perturbation, and it sits at location theta plus 1 over theta as soon as theta is more than 1. And when theta is less than 1, you don't see an outlier. You just see the eigenvalues between -2 and 2. Yeah. So this is a very classical model. This is called the BBP transition. And for Gaussian random matrices, this can be studied using classical tools in great detail. Okay. Now let me ask a very stupid question. Suppose that I now replace all of these Gaussian random variables in here by Bernoullis with very small p. So I take very, very sparse random matrix, right? Let's replace Gij, these are Gaussians with mean 0 and variance 1, by some kind of, let's say, epsilon ij, delta ij, where epsilon ij are plus or minus 1 with probability 1/2. So this is just a random sign. And delta ij is 0 or is 1 with probability p and 0 with probability 1 minus p, right? So this is Bernoulli p. But I'd still like them to have variance 1, so let me divide it by the standard deviation. Right? So I've standardized them so that they still have mean 0 and variance 1. Right? But if I take p to be very small, then most of the entries of this matrix will be 0, so it will be extremely sparse. Right? And now the question is, how sparse can you make this matrix and still see the same behavior? Well, it seems like something that should be within the reach of classical methods. And in fact, I think that because if you're really studying the asymptotics of these models, really as an asymptotic theory, you could probably use some kind of classical universality principles to study the same question. Okay? But in fact, when I looked in the literature, the first time I saw a paper approving anything about this was in 2001. Okay, and using heavy machinery and going through the proofs and doing some complicated combinatorics with non-backtracking matrices, all sorts of heavy work. Right now, in principle, for us, you see, if you think about this from the perspective of our theorems, what do you see? Well, actually, this matrix, when I make this replacement, I haven't changed the mean and the covariance of the entries of the matrix. Right. So actually, when I make this replacement, then the Gaussian model is just the original random matrix I have here, right? And the new model is the sparse one, right? Has the original random matrix as the Gaussian model. Right? Now, in this case, what is the size R, the size of the entries? This is of order 1 over square root d times p, right? The square root p comes from here, the square root d comes from there, right? Therefore, if you just plug this into a universality result, you get this exactly the same BBP transition, right? So you get exactly the same picture that I'm showing you over here. As soon as P is much, much larger than some power of log D over D. I think maybe log D to the 4 over D or something like that. You get it completely for free. This is nearly optimal because around log D over D, right? If P is much less than log D over D, then the entries of the matrix become disconnected. The graph of the entries become disconnected and the matrix behaves completely differently, right? So the best you could hope for here is log D over D. And here you see, okay, we paid a little bit in the power of the log, but we are already in an extremely sparse situation. And we basically get, I mean, it's a one-line computation to show that if you apply the theorem on the previous slide, that the BBP transition extends to this situation. So in many ways, this is not a very good example because this is an example with basically almost IID entries, right? The noisy part of this matrix is IID entries. So it's almost classical random matrix theory. But I'm just trying to illustrate how, once you have the general tool at your disposal, questions that otherwise might be difficult actually become kind of trivial applications. You can just hit it with the hammer and you will get something pretty good, right? It may have a slightly suboptimal power on the log, but otherwise it seems to capture exactly what is going on in this situation. And it's something that up to now seems to have required much heavier tools to prove than just blindly applying a black box. Okay. But how much time do I have for another application?
You have, we started 2 minutes late. You can speak 4 or 5 minutes.
Okay. So let me just do one more quick application. Again, a rather simple one. Okay. So I'm not really making here in these applications full use of the power of the theorem. Okay. Because I'm not really introducing dependencies in the Gaussian model. I'm not using heavy machinery about Gaussian random matrices. I'm just trying to illustrate how easy it is to apply these results and how easy it is to get non-trivial results. Okay. So this is a model of random regular graphs. So a regular graph is a graph where every vertex has the same degree, right? So you can pick them randomly, of course, and this is a classical model in discrete mathematics. And in fact, there are many different natural models of random regular graphs. Yeah, this is well known. There are many ways of drawing random regular graphs which have slightly different distributions. And the classical way of studying these graphs is to fix the degree and let the number of vertices go to infinity. So now I'm going to be a bit confusing because up to now I've made the dimension of my matrices D, but now I'm going to make the degree D. This is just standard notation in this field, and N is the number of vertices. All right, so now we're going, if the adjacency matrix is now going to be N by N, not D by D. Okay. So typically, when one studies random regular graphs, what you do is you fix the degree. Let's say I take random regular 3 regular graphs, right? Where every vertex has 3 neighbors. I pick them randomly among all 3 regular graphs and N vertices, and I let N go to infinity and see what happens. Okay. So these kind of questions are very interesting, and they are. There's been a lot of literature studying these kind of problems. And what turns out to happen that when the degree is fixed, all of these different models of random regular graphs turn out to be more or less the same. They're at least contiguous, which means that most answers of things that happen with probability 1 are the same in all of these models. But you might also want to understand what happens if you allow the degree to diverge with the number of vertices. And it turns out, I was actually very surprised about this. We learned this from Yizhe Zhu, is that there are many things that are not known about this. There's some survey by Van Vu about discrete random matrices from, I think, 10 or 20 years ago, where he poses this question about whether certain questions about random regular graphs the answers remain true if the degree diverges. And apparently it's still open for in many regimes and for many random graph models. So let me explain one very simple model of random regular graphs, so-called permutation model. So this is actually a model of a random regular multigraph. So it can be that there are multiple edges between the same pair of vertices. So what do? The adjacency matrix, you simply choose it to be the sum I is 1 to D of pi I, okay, where pi I are IID N by N random permutation matrices. So I just pick N by N permutation matrices uniformly at random. I pick D of them, D is the degree, and I add up these IID random permutation matrices. So if you do this, you can easily check that every row, the sum of every row and the sum of every column will be exactly D. So this is the adjacency matrix of a D regular multigraph. If D is fixed and N goes to infinity, the probability that any vertex will have any pair of vertices will have more than one edge will become very, very small. And this just behaves exactly like any other random D-regular graph. But when D diverges, of course, you will have non-negligible number of vertices with pairs of vertices with multiple edges. So when D is fixed, it is known that the norm of X, not just an expectation, just the norm of X, converges as n goes to infinity to 2 square root D minus 1. This is a very famous result. This is the spectral gap of the D-regular tree. Okay. And now the question, I believe by Van Wu, is this still true when D diverges? And I mean, from my perspective, this is a trivial question, as you will see, but as far as we were able to check in the literature, this seems to still be open. At least as far as I could tell, in most regimes, this is still open. Maybe when D grows very slowly with N, it's okay, one can adapt the proof. There's a paper by H.T. Yao and his group from a few years ago where they wrote that this is open. So, I mean, it seems to be open. Now, what can we say about this? I really don't have to write anything. This is a sum of IID random matrices. So that's like the kind of model that's perfectly, I'm lying to you here a little bit, of course. This should be the X minus its mean. The norm of X, this is a D-regular graph, right? The norm of X will be D. That's the Perron-Frobenius eigenvalue. Well, one is interested in the centered version. So, okay, this is a sum of IID random matrices, very non-Gaussian, but nonetheless, right, fits perfectly into the general model that we have. What's the Gaussian model associated to this matrix? Well, I mean, you could just compute it by hand. It turns out that the covariance between the entries of this matrix is 0. So just a Wigner matrix. So if you apply, if you just blindly apply the theorem that I wrote down, what you will find is that by this universality principle, you will get that the expected norm of X tilde minus the expectation of X tilde, right, is 1 plus little o1 of 2 square root D when D is much larger than, let's say, some log n to the 4th. So in particular, it actually gets easier. When the degree is larger, this problem should get easier, not harder. But the usual proofs of these type of results get harder when the degree gets larger. But as soon as you exceed some small power of a log of the number of vertices, then basically our results show that these X tildes behave exactly like Wigner matrices. And for Wigner matrices, we understand exactly what the distribution is of their, what the edge of the spectrum is doing, etc. Right? So again, I don't think that the thing about this example is that it's very deep or it's a very interesting special case of our results. But the fact is that when you have a kind of result like this, or a question like this, that at first sight looks like it requires some special work, when you take the kind of right viewpoint and you use the right box, it turns out to be very easy to get results about these kind of matrices. So of course, it would be very interesting to have universality principles that extend to more general kinds of non-Gaussian matrices that do not fall within the framework of matrix concentration inequalities that I showed you. And I think more can be done, and we certainly have ideas about this and ongoing work about that. But at the very least, I hope to have given you a flavor of the kind of things that we can prove and can do with these kind of inequalities, and that I think this is a natural way to think about nonasymptotic questions that goes in a kind of a slightly different direction than the usual approaches that are taken in this area. So let me end there. Thank you.
Thank you very much, Ramon. That was a very nice talk.